Hey, what's up guys, my name is Cherno. Welcome back to my code review series where we've been looking at a path tracer made by a 15-year-old in C++ and OpenGL for the last two videos. Last time what I really wanted to take a look at was the rendering. I wanted to see how this image comes together and more importantly, show you guys how I go about discovering that for an application that I clearly didn't write. However, we got sidetracked with fixing the camera because the camera was a bit annoying. Anyway, go watch that video if you want. I've linked it up there. So today, with that fixed and out of the way, what I want to do is take a look at how we go about producing this image. How does this application render this? Where do I even begin if I want to know exactly how this happens? Now, the most obvious choice to, I think, most people would be to just look at the source code. Because if you have the source code, if you have the shaders, you basically have everything. You physically have everything you need to discover how this works. The problem with that, where do I even begin? It's not that it's bad to do that. I think it's okay to do that. But I see, well, let's just say two major problems with that. The first one is the fact that code is not usually written in a straightforward way. I mean, even in this project where most of the code that we care about is written right here in this main.cpp file. I mean, like literally almost everything is in here. Everything from the creation of like the window to us loading with like which shaders are we loading. How is like the key stuff handled? What are the resources that we're setting up, like textures and frame buffers, and all of the OpenGL code that we're running? I'm not sure if all of the OpenGL code, but there's a lot of OpenGL code right here inside this main file, as well as like here's like IMGUI stuff happening as well somewhere. The shutdown, like a lot of stuff is in this main file, which isn't generally the case for larger applications. But even in this file, it can be a little bit difficult to clearly see how we end up with the aforementioned image. The reason why is because even if we just search for GL and we look at all of this stuff, we have to obviously go through a whole bunch of different code. We don't know what branches are being hit here. We don't know how many number of bounces there might be. So how is this happening? We have to try and hunt down every single resource and see, like, for example, what format is it in? And you can imagine that we also have to basically sort through this person's render API. So there's this post-process shader, which is a shader object. So if we want to see, for example, like how this is being set into the shader, well, we have to go to this function now. And then like sort through all of this code. There's a lot of sort of spelunking through code trying to decipher an API that we're not familiar with. Doing it that way, in my experience, I've been programming for, I think 13 years now. 2011 is when I seriously started like learning my first language. And honestly, I can comfortably say that 13 years later, I will do this and I will still miss things. There'll be so many things that I will just miss. I won't realize that something is happening and I'll try and look for it and it'll either be really hard to find or I'll be like, oh, I guess they're not doing this. But then later I'll discover that I was wrong and I've wasted half a day trying to look for code that, you know, basically blindfolded because I'm not familiar with it whatsoever. The thing about programming and C++, I'll say potentially specifically, is that things can be complex. Things can be indirect. You might not realize that certain code is being invoked from, I don't know, additional libraries, for example. So the actual code might be even hidden in a compiled format in a DLL or something. Like you might not realize that actually there's something else that's happening that I don't even know is happening because it's not directly inside this code. In order to comfortably sit down and be like, yeah, I understand every single thing that is happening inside like this renderer to render that image, that's a really difficult statement to make. Now that was like the first problem. The second problem here is obviously just by reading this code, physically reading it, we do not know like the values of variables. All that we see here is really a bunch of English words. Default shader, U1F, focus distance, my GUI.focus distance. I mean, as a human, I can read that and be like, there must be a shader called default shader, which is, you know, default.frag and default.vert. And then I'm setting a variable that seems to be called focus distance, a uniform called focus distance. It's a single float. And this is the float that it's being set to. And if I look at the float that it's being set to, I can see in this case, it has a default value and that's 3. So I can be like reasonably sure, maybe not really, but I can have an idea that perhaps focus distance will have the value 3. That's just one example. What about something like do bloom? Like, is that being called? Okay, well, it's false by default, but what if something in the UI changes it? What if something in this program changes these variables so focus distance might not be 3? What if it's being loaded in from a file? If I'm trying to figure out how that particular frame is being rendered, clearly this is not very easy. Now, the simplest way to probably get around that is just to run the application. I actually have a whole video about how you can read like C++ code a lot easier. I'll have it linked up there. I talk a lot about the importance of actually running the code that you are either writing or reading in that video. However, it's still not like an ideal way to see what's going on. So to summarize, the reason why I don't like to simply read the code is because, first of all, I have to sort through whatever API this person has written, whatever abstractions they may have made. I can miss things very, very easily and make mistakes. But then also, too, I don't really have a clear view of the data. And the data is very important because at the end of the day, our computers are simply taking one format of data in and outputting another format. We're taking in a bunch of variables, doing some calculations on them, and we output the image that we see. So what I'm trying to say with this is that data, that blob in the middle, the data, that is the most important part. That is the most important part of your program. The transformation that's happening to that data, clearly very, very important as well. But without the data, there wouldn't be anything to transform. So it's very, very important to have a clear view of that data. And that is what we're going to talk about today. We're going to talk about how to see this in a much more easy way. We're going to be using a graphics debugger to just capture a frame. And that way we can analyze it. We can see exactly what OpenGL calls in this case are going into that, what data we're using, and how the frame comes together. But first, I want to thank the sponsor of this video, Brilliantorg. Now, for those of you just getting into your programming journey, I really think this can be super helpful to you, and you can get started for free. So hear me out. Brilliant.org is an amazing website filled with lots and lots of really high quality courses on various STEM topics. So STEM, science, technology, engineering, math, is that what it stands for? Yes. Yes, it is, which is great because that's the field of what we're doing here. It's not just computer science and technology. A lot of this revolves around math. Like the ray tracing images that we're seeing here are mostly able to be created because of mathematics. And Brilliant has some really great courses on all of those topics. If you're just learning programming and you're trying to figure out how programs come together and how they're like logically written, Brilliant has some really good beginner computer science courses that will teach you how to think like a programmer in a really kind of visual way that you can actually interact with. And since math, as I mentioned, is, like really important for programming, it's really, really good that Brilliant's courses extend into that realm and they go down all the way to this everyday math course that's fantastic if you're a beginner at math, through to things like linear algebra and calculus, but again, teaching these things visually and with widgets you can play with to understand how these numbers are having an effect, whilst also quizzing you along the way to make sure that you're learning and retaining this information. And you can try it out for free because Brilliant has a 30-day free trial that you can use to explore their entire platform, see what they have, see if you like it. And if you do go on to like it, Brilliant have been nice enough to offer the first 200 subscribers 20% off an annual membership. Huge thank you as always to Brilliant.org for sponsoring this video. So how do we hook up a graphics debugger to this application to see how it works? So first off, we're going to be using something called RenderDoc, which you can download for free. Here is renderdoc.org. I'll leave a link in the description below. It's open source, which is really nice. And it supports like pretty much everything. Vulkan, DirectX 11, OpenGL, DirectX 12, Windows, Linux, Android, Nintendo Switch even, which I didn't know, which is great. It's really cool. And one thing that I do like about it is that like you can just hook it up to any app. Like this doesn't have to be an application that you have the source code of. No. You can hook this up to like, a commercial game and actually dissect it and see how it works. We're getting a little bit sidetracked here, but an example is, this guy, Adrian, who does these graphics studies. So here's like a frame of GTA 5. He's gone through and actually like shows how this rendering works and all the different like diffuse, normal, specular, radiance passes that we have here, or other attachments that it's rendering to that we have here, part of the G buffer. Depth and stencil, you can see how the different values of the stencil buffer correspond to like different, I guess, IDs. Anyway, I'm not going to go through this now, but the point is it's really, really cool how you can take a look at this. So RenderDoc is not just useful, for debugging your own applications or stuff that you've downloaded source code to. It's just a really good learning tool that you can use. The other main graphics debugger that I use is NVIDIA Nsight, which in my honest opinion is a little bit better, but it's more complex, which is just not necessary in a lot of cases. Sometimes you just want a nice simple view of things. And also it's NVIDIA only, whereas this works with AMD and Intel, which is great. But because it is NVIDIA specific, you can go a lot deeper into like your analysis and into things that you're debugging. And also it tends to be more correct. So sometimes RenderDoc will give you values that are just not true. Nsight will do that as well sometimes. but less so usually than RenderDoc. So those are the two that I use. So today we're going to use RenderDoc. So how do you even use this thing? So if we go to launch application, the first thing that it's going to ask for, and Windows, I think, has this launch application thing. So if it's not here for whatever reason, it'll be under this menu. So there's two things that we care about, possibly three. And I guess it's the first three here. So executable path is just a file path to your executable. So what program do you want to run through RenderDoc? Working directory is really important. This is where a lot of people go wrong. I probably should make a video just talking about working directories in general, because I feel like universities don't teach like what a working directory is, and then like students will struggle the rest of their introductory semester like of programming. But anyway, working directory, the reason why this is so important and people get this wrong is because if you're used to running things through Visual Studio, or you download a program that's running through Visual Studio, then a lot of the resources, the assets that you have will be relative to the working directory that you use from within Visual Studio, which by default is the project directory, not the binaries directory where you actually build your executable to. So if you leave this blank, it'll use the same working directory as the exe, which might not work because your assets might not be present like relative to that directory. Command line arguments, obviously if your app has command line arguments that you were using from within Visual Studio, or if you run it as an executable, you'll have to put them in here as well if you want that same result. Okay, so executable path, how do we get that? Well, when we build this, so if I just right click over here and hit build, I've moved the solution Explorer, by the way, over to this side with the face cam, just because I feel like this area should contain the code when I'm making videos. I think that's where Visual Studio puts it by default. I really like it on the left though, but anyway, we won't talk about that now. So if you just right click and build this, you'll get in release mode, might I add. Usually I like to use a release configuration when doing this stuff, just because it tends to run a bit quicker. It's a bit more optimized, that kind of thing. I've already built this, but otherwise the cool thing about build is it will actually tell you what the path, like the executable path that it spat out. So let me just rebuild this so I can show you what I mean. Okay, so you can see over here that like this project file was basically built into this executable. So all of this is just like in a little effort to optimize how we get this path. Instead of us going to like the project directory, then trying to look, especially if it's not your project, trying to look in where it outputs the built binary, you can just copy it from here. The other place is if you go into debug. So I've run this, right? So if you go into debug up the top, you can see that like the first thing it loads is this. So two different places where you can actually get the absolute path that's going to the executable that you want to pass through RenderDoc and actually analyze. So we'll copy that. We'll go to RenderDoc. We'll paste that exact path in here. You can see by default, it's using the directory that contains the executable as the working directory, which we do not want, because we want to use the same working directory that we were running it through in Visual Studio, which if we just go to the properties of that, I've hit Alt-Enter there, but you can right-click and hit Properties as well. See, it says Alt-Enter here. So over here inside the debugging, and you can set this to all configurations, and this really doesn't like my screen scaling that I use for recording videos for whatever reason. I feel like it's like this is Windows 11, we're in 2024 now, and still just does not seem to work everywhere, even in Microsoft's own products like Visual Studio, which is just crazy. But anyway, you can see the working directory, actually for all configurations here, is set to the project directory macro, which maps to this directory, which is the directory that holds like the project. So if you right click and hit open folder in File Explorer, which will open this folder with the VCX file. So we need to get the path of this and paste it over here into our working directory. And there are no command line arguments, but that's all you need, just these two little things. And then we can hit launch, and it should launch our app in the exact same way that it would have been launched through Visual Studio. So now you can see the difference here is it says capturing OpenGL. Here's the frame number. Here's like the milliseconds per frame and the FPS. You can see it says F12 print screen to capture. So either F12 or the print screen key can be used to capture a frame. So what we're going to do is, first of all, set up the scene that we want to analyze. So we'll go to Many Spheres 2, and I'm going to hit R to switch this to the kind of path tracing mode and not the whatever was before. And then let's just like, we'll put this into like a nice place. It doesn't really have to be in a nice position, obviously. And then I'll wait for it maybe to accumulate a bit. I don't think it's going to matter for app purposes what state we capture it in, but at some point I'm just going to hit F12. So I've hit F12 now. It should have captured a frame. I can actually see that if I just move this aside, and there it is. Frame number 7,342, 51 megabytes of data. That's what it's captured. Now I can close this, or I can capture more frames if I want. I can leave this running and just open that capture. But if you close your application, it will automatically load the most recently saved capture, and we are taken to this view here. Okay. So, where do we begin? Because this can look a little bit intimidating. I'm probably not going to make this a full-on RenderDoc tutorial. The reason why is because I actually don't think this is a good test case for RenderDoc. This is like not like a, a complex rasterized scene or whatever with a lot of objects. It's literally just, a fragment shader that runs some code that renders this image. So I don't think it's a great example, but I'll explain things as I go and I'll show you the most kind of important things that we have. So event browser. And timeline. So timeline, you can see, shows every single kind of event that goes from 0 to looks like 112, it says over here as well. And you can see also in the event browser that these things basically map together. So if I click on one of these, the timeline goes to that spot. And if I drag across the timeline over here where the numbers are, it also will go to the event that we see over here. What this is for that frame, it is every single render API function that you called or that was called. So you can see over here that we have a list of start kind of from like the beginning of the frame to the end of the frame of every single OpenGL function that was called. So you can see how immediately, even just that is so great because I can immediately see I'm not going to miss anything. I'm not going to miss anything because it was abstracted behind some other, class or in a different file. It wasn't in the main file, or maybe it was even in like a plugin or a DLL or something, and I'm not going to see that at all. It's black box. No, everything will be here. Everything will be here, and I can flip through it and I can see what it does. And there's a lot more you can see in a minute, but I just want to stress that at a minimum, you can see that this is immediately really useful because I can see how this frame comes together from pure like API commands. Now, if I wanted to see, for example, how many draw calls are there or how are the draws happening, I can just type in to this filter the word draw and it will show me all of these draw events. And draw is a good word, I think, to type in because it will capture, like it'll include the various different draw calls that OpenGL might have, like draw arrays, draw elements based vertex. Obviously, if I just type in like draw arrays directly, it's just going to show me this stuff, which isn't going to include potential other draw calls. So draws are generally good word, even though it will give you some false positives, because you can see GL buffer data here was actually used with stream draw. So it's also including that. So just like that, I'm able to see 1, 2, 3, 4, 5, 6, 7. There are 7 draw calls that make up that frame. This stuff, all the stuff that's under color pass, so you can click on this to expand it. All of this stuff is actually like IMGUI. And you can see, by the way, inside this texture viewer window that it usually flips to automatically, you can see if I drag it from the beginning through this timeline, you can see the frame coming together. Again, for this example, it's basically like nothing. And then a single draw event, this first draw arrays actually produces this image straight away because it's a path tracer. The fragment shader is really just being used kind of like a compute shader to just calculate some pixel values and write them to a texture. So it's all immediately done inside that single event, which you wouldn't see in a rasterized renderer. However, if we go to, a little bit further, we can see that, oh, look, there's like our scene collection window. This is the draw call, draw elements based vertex with 375 indices. That's what gets called to actually draw this. And this is the first part that gets drawn. The next draw call, you can see it draws like this label and all of this stuff inside a single draw call. Then we have this window being drawn. Then we have that. The window stuff inside there being drawn, we can see how the frame comes together, which is really, really useful. But that's obviously not only what we can see, because that's great for seeing the process. That's great for seeing the stuff that we theoretically could have just read from the source code, obviously. May have been difficult, but definitely possible. It's all there. What's the other important part, apart from just the commands and the code? The data. So that's the great thing about this, obviously, is that it includes all the data that was used to make this frame. So if we go to this draw event over here, which as we know, because if we go back one, we can see that this one is, let me just clear this so that we can see what this actually is. You can see this is the GL clear. Some of the like significant draw events you can see will like draw events that affect, I guess, the texture viewer or like have resources to show you will generally show up over here. So they're showing up as these little blue things. You can also see that there's a bit of a like a legend here, I guess, that shows some of the stuff that's, I guess, happening. But generally these things are just usually like draw calls or clears or stuff that writes data to resources like this, for example. It could also be like a compute shader, something like that. So over here we have GL clear. So we just clear it and we can actually see just by looking at these parameters what we clear it to. But then if we go to the next one, it's this draw arrays. So generally all of these draw calls are going to appear over here in this timeline visually. Now, on the left side, we have inputs and outputs. At a glance, this is probably really all you need to look at. It's a good first thing to look at because it shows you that, for example, into slot 0 over here in the fragment shader, we have this skybox bound. If you want to flip it, by the way, because it's like upside down or whatever, there's this little flip button, which is nice and useful. We can actually go through and see, for example, that it has no MIPS, because this is grayed out. Visualize different channels if we want. There's a bunch of tools here that I won't go through now. And then there's this texture. And this texture that we're taking in here looks like the thing that we're actually outputting. So if we go to outputs, you can see texture 61 and this mysterious texture, which, what is that? We'll find out in a minute. But they look similar. And that's because I think we discovered in like the first episode, maybe that this, like to be like a progressive path tracer, this will actually take in the previous frame's output and then combine it with the current frame's calculation so that we basically get more detailed and more realistic results because we're progressively accumulating these samples, progressively tracing more paths, but it's over like several frames or over really infinite frames as long as we leave it running for, which is typically how like path tracers work, because that way it can show you the result basically as it progressively accumulates more and more light samples. But anyway, so that's great because we can already see that. Now that's cool. And that's the texture viewer, which you can see, by the way, you can go through, as I mentioned, the MIPS. So you can see there's nothing actually in MIP 1, for example. It's just all in MIP 0. If it was a cube map, you could look at all the different faces to see what they look like. But if we go over here to the mesh viewer, that's another interesting thing to look at. Potentially not for this example, but you can still see that for this draw call, we are drawing 6 indices, as we know. Here they are. We can actually see what they are at the Vertex Shader input and output. So what it is before the Vertex Shader processing and what it is after, which you can see here, it's unchanged. And then you can have a look at, it actually will highlight one of them, and I don't really like the way this camera works. But anyway, I won't worry about it here. And you can shade it like solid, for example. So we can see basically that we are drawing like a quad. It looks like we're drawing a square because that's what we're looking at over here as well. And you can also look at Vertex Shader out, which, as you can see, shows us what it is after that Vertex Shader transform. And it looks like it's just like on the screen directly, because this is just a bunch of vertices. You can orbit around it, but this is basically what it's going to be outputting. So we can see that this is drawing a full screen quad pretty easily, which is really, really nice. Now, pipeline state is the other really, really important one, because what this shows you, as you can hopefully see, is an overview of every single stage in your pipeline. There's also this compute shader over here, which you can see doesn't have any arrows connected to it, because that, of course, is a different pipeline. There's a compute pipeline and there's a graphics pipeline. And this is showing you all of the different stages that you can look at that are part of this graphics pipeline. And of course, in this case, we are using the graphics pipeline. We're not using compute, which is why you can see that the stages that are in use, you can see are like this kind of lighter color. So we have a white color versus a gray color for things that weren't used. So like you might have like a geometry shader that's not in use, or tessellation stuff. And then that's why this compute shader is also grayed out, because of course it's not being used. But we can click on all of these different ones that are used and see what they're actually doing. So like vertex input, for example, we can see that we have an attribute, because there's vertex attribute formats, called apos, and it is of this format, which basically just means it's a vec4. It's 4 floats. We can see different offsets if we need to. Really good, again, for debugging. Buffers, so this would be our vertex buffer with a stride of 16 and a byte length of 96, so we can see what it is. You can hit this arrow near go to actually see the contents of the buffer. Vertex shader is the actual shader that is running now. So we can look at the shader and what data is basically being used or consumed by it. So first of all, you'll notice that there are no textures, no samplers, and no uniforms or uniform buffer objects. So absolutely nothing going into this. If we hit view over here, we can actually look at the shader source code. So we can see now why, first of all, the before and after Vertex Shader vertices were identical, because all it's doing is basically just setting a position into gel position, just making sure the W component is 1 here, because we're taking it in as a vec3, but it's not changing the data whatsoever. And of course, there are no uniforms or textures or anything else, as you can see from this shader code. So immediately, just at even a surface level, we just know that part of drawing this image, this is the exact Vertex Shader that's running. There's no like shadow of a doubt here. There's no like, maybe I read the code wrong and am I sure it's this shader? No, we can see all of it here, and we can be sure that that's what's happening. If we go over here to the rasterizer, this just has a few things that, control how it's being rasterized. So how are those vertices being converted into pixels? How is it being filled in with pixels? Things like the fill mode and multi-sampling and culling and like, scissors states and whatever that might be. And that will lead us into rasterizing it. And for each pixel, of course, we'll call the fragment shader, which is where we would expect most of the meat for this image will happen, since the fragment shader, as I mentioned, is being used basically as a compute shader to just process all of this data and spit out some colors, which are the pixels that make up our image. So inside the fragment shader, there's stuff here now. So first of all, again, we can hit view and we can look at this code. So we know this is the shader that is being run. It's quite a lot. There's like 385 lines of code here. So it's definitely doing some work here. And then if we take a look at the pipeline state once again, you can now see that there are two textures bound, slot 0 and slot 1. We also saw this, by the way, in the texture viewer in the inputs, but here they are inside the pipeline state with some more information, such as like the width and height. Another really cool thing though, is you can actually click on this arrow here where it says go to look at the resource, which is showing us over here. And if you go to the resource inspector, if you're inside the texture viewer, you'll probably have to like right click on this maybe and do open in resource inspector. But the resource inspector will show you a list of all the resources over here, which is really useful. But also for texture 60, which is what we opened up, we can see how it was created. So you can see there was a call to GLGen textures to create it, then bound it, and then check this out. We can see how the sampler was set up. So what the wrap mode is, so it's repeat, what the minification magnification filters are, so they're just linear, the format that it was created with. So you can see the format is GLRGB, with the internal format being GLRGB32F. So we know internally it's being stored as like an HDR image. Really, really useful stuff. And then here are the samplers that are being used to sample these. In this case, they're going to be the same. So we looked at this one being repeat and linear. But then down here in uniforms, if you look at the shader code, you can see there's a bunch of uniform values here inside our C++ code. There was also a bunch of uniform variables that were being set here, but yet inside this view, there is a little go arrow here, 21 variables. And if I click on it, check this out. I can see every single uniform variable that is being used by that shader with its values right over here, with the exact values that were used for that frame that I just captured. So this is super useful. Especially when you're debugging your own programs and you're not sure, for example, if the variables are even getting to the shader, you can visualize them as colors. That's a common thing to do, but also you can just look at them here and make sure like that they're correct and what they are exactly, which is super useful. So we can see that focus distance is in fact 3, as the default variable that we looked at earlier seemed to imply. So this is great because it's so nice to just be able to look at all of this in one place without having to hunt down certain values, or even if you were breakpoint debugging, having to look at that uniform buffer or like all the destructive data that might be there, every single variable, trying to hunt it down. Because in more complex projects, all of them might not even be set in one place. And there'll probably be multiple. There might be different uniform buffers that might be used. There might be storage buffers that you might need to look at. All of this stuff can easily be accessible just within this one view. And you can be sure that that is the data that was used to create that exact frame that you're interested in inspecting. So that is super, super useful. I will say one other thing. This is also useful for like, if you've ever found like a cool shader on GitHub or just a cool graphics project maybe on GitHub, and you're trying to basically steal it and use it in your stuff. And then you see just like a whole bunch of uniform variables and you're like, ugh, like, I don't know where you're setting this in your C++ code. I don't know like how this is even working. I can't just take this shader, right? Because I need to know what these variables are, because obviously they make up the shader. I need to know what the values are, or at least what sensible defaults maybe that I can set them to. And that's where this is great. If you can just run it through this, then yeah, these are the values that were used. You can see the visual result of using these values, and you can be happy to at least use these as like a starting point so that you can work your way forwards from there. So really, really useful for that as well. And again, this is a simple project, so this is not potentially showing that much, but obviously if you had different storage buffers or different other resources like textures bound that you wanted more information on, you can see them all over here, which is really useful. So if we move on to the final stage here, which is this like frame buffer, I guess, stage, this is like where it actually writes these pixels onto the frame buffer, this mostly shows things like the blend states and what attachments we're writing to as well. So you can actually see that we're writing to 2 different attachments here. We're writing to slot 0, we're writing to slot 1, and this is the resulting image, which we can go over here into the texture viewer and actually look at. So over here in outputs, there it is, texture 63, and that's what it is. Now we know from the pipeline state that that of course is being written into slot 1 over here. So if we go back to this fragment shader and hit view, we know that it's going to be this bloom color. So that's what's happening with the bloom color. Here it is being written out over here, and we can just take a look at what exactly that looks like. So you can see that this is like the main texture that we were writing out and looking at, and then this is just that bloom texture. So it's filtering out just the brightest pixels, which, by the way, if you right click your mouse and just drag it around, you're sampling all of those different regions. So if I just right click on this, you can see over here what the value is. And at the moment, it's just saying 111. So that is the RGB of that particular pixel, which, might I add, is not a good thing, because you can also see that this texture is RGB 8. So this is actually like a standard, I guess, dynamic range image, which is not correct. So you actually shouldn't be doing this. Same with this one. This one's also an RGB 8 image. Now, the problem with doing this is that we don't really have an idea on the exact brightness of these pixels anymore, do we? Because you can see that they're all just simply either 0 for the black regions over here or 1 for the white regions over here. So we definitely need some idea of exactly how bright they are, because certain parts of this image, like this part here, will probably be not as bright as this part here that's facing the light a lot more. But we can't see any of that because they're all being clipped to 1. So you can see that just by looking at this for a couple seconds in RenderDoc, I'm actually able to immediately find a bug, we'll say, with this renderer, and I can immediately give a suggestion to, yeah, maybe change this to an HDR buffer, and then that way you can have some pixels being brighter than others, even though they're past that range. If you really want to stick to an RGB 8 image for whatever reason, there is no reason, to be completely honest. In this case, this is running on PC. This 2024, like, that's fine. Maybe if you're on like some mobile hardware back in the day and they either didn't support that, or you wanted to save your GPU bandwidth or something like that, and you really wanted to keep them as RGB 8, you didn't want to expand them into like a 16-bit or 32-bit floating point format, because that would obviously take more memory, more writing, all that stuff. Then what you could do as a little hack, when you write out the data, you could do a couple things. At the very least, you could just do like data -1. Because what that's going to do is going to give you an entire next step of range. So for example, my point is, if one of these pixels was 1.2 and one of them was 1.5, if you write them out as is, you'll get 1.0 in both cases. But if you subtract 1 first, you'll get 0.2 in one case and 0.5 in the other case. So you're not losing that data. You can restore it by simply adding 1 later on. Now, that's a very primal way of doing things, and slightly better way might be to actually scale it. Because the problem with this case is that you might have something that's 2.5, something that's 3.5, something that's 14.2 or something, and you're going to lose that, because everything, like, this will be 1, this will be 1, this will be 1, but then this will be 0.5. And then this will be 0.2. So you'll retain these two, but you'll lose the rest of your data. Whereas if you multiply them by like 0.1 or something, you're going to get some more information. And then maybe that will be 1, this will be 0.35. Now you have to remember though, it's RGB8 and these are going to be integers at the end of the day. So 0 to 255 is really the range that you can store. It's just that what I'm doing is slightly mapping it so that you use that full range instead of just basically doing a 1-bit texture, which is what's happening here, right? You can think of it that way. If we have 8 bits to use, let's use those 8 bits. Here we have 1 bit. We basically have either 0 or 1. Black is 0, white is 1. That's it. Let's expand it, use it a little bit more. Even though we know that in this case we have 256 different possible values, we don't have kind of infinite-ish if we were actually using a floating point format and we could use like decimal values and stuff like that. Anyway, I hope that this video was useful for you guys who might be looking at other people's application or even debugging your own graphics applications and you're not sure what values are. You want a better way of looking at what's actually going on inside an application. Using a graphics debugger like RenderDoc is super, super useful. Thanks to us using RenderDoc, we can now be fairly certain that this particular pass over here, this GL draw arrays that we have here, which we can easily locate within the source code over here, we know that this is the exact bunch of code that is producing that image that we're actually seeing over here. We don't have to guess and hope that we're right. We've actually tested this and we are sure that we're right. And I think that in itself, honestly, is the way that computer science should be done. In the next video, in this like path tracing code review series, we're gonna look at the actual code that runs and creates this image. I'll give you guys a walk through the actual GLSL code and we'll see if we can find any problems. Thank you guys for watching. Don't forget to check out Brilliantorg/Cherno and I will see you next time. Goodbye.